That you see the
Okay, so we've covered pages 1 through 8, and then 13 through 18 was the review from the previous part 1 of the multiple choice test. And I think we started page 9. But if you look on the board here, Thursday's test is going to cover second semester topics, so pages 9 through 12. And then I'm going to save that page 19 through 22 for morning review. Now, I'm not going to be able to do a morning review on Thursday because I have to proctor the biology EOC and I have to do a whole lot of setup. Won't be able to have a dedicated time to do a morning review. However, I will do a morning review tomorrow, going over pages 19 to 22. So I'll send out a link tomorrow morning. But if you want to be in the classroom, you can be in the classroom at 7:15, or you just join on Teams. I'll send out a link tomorrow morning, or if you just want to watch the video later, you can do that as well. But morning review tomorrow instead of Thursday. I'll send out a reminder this afternoon. Okay. So these are all great topics here on page, or good problems here on pages 9 through 12. But let's do this here. Let's just pick one of, I think we did 1 and 2 on page 9. So let's do, let me see. Let's do number 4. I think number 4 is a good indication of a specific theorem here. So number 4 says uppercase f of x is a definite integral from tangent to 0 of dt over 1 plus t squared. Find f prime. So if you look at f of x has the integral as part of its function. So if I want to find the derivative, then I have to involve the derivative of that integral. So let me just go ahead and set this up then. If I want to find f prime, that's the derivative of this mess. Now we could find the full antiderivative of that and then turn around and take the derivative, but there's a bit of a shortcut, right? And what's that theorem that we can really apply here? You guys remember this theorem here? What's this theorem called? This is the second theorem, yeah. So second fundamental theorem of calculus. Now, how can we tell whether that we want to use second theorem? If you have two operations that are lined up to apply onto the same expression, that's a good indication, right? If I want to find the derivative of an integral, that's an indication that we can use that shortcut method to kind of jump to the end without having to do both processes and go forwards and backwards. So we can apply second theorem here. We know these two operations will cancel each other out, but something feels a little bit out of place. We notice about the bounds. We want the lower bound to be the what? Like the constant, right? And the upper bound to be the variable, right? So can I flip the bounds? So anytime I flip the bounds, what needs to occur? Change the what? Change the sign, right? Okay, so I can do that. So second theorem, we can skip all the process and just basically jump to the end. So it tells us to do f of p of x. So what does that mean? take the tangent of x and do what? Put it in for t, yep. So -1 over 1 plus tangent square. So that's nice. We don't have to do any calculus procedure here. We're just plugging directly into the expression. Times what? Tangent's derivative, which is secant squared, right? Now, there's a bit of a identity here because 1 plus tangent squared is secant squared. So if I multiply this out, I get negative secant squared x over 1 plus tangent squared x. And 1 plus tangent squared x itself has a special property. 1 plus tangent squared is secant squared. So if I have negative secant squared over secant squared, that's equal to what? -1, yeah. Yeah, so a lot of second theorem, a lot of use substitution that's coming up. But I really want to make sure that we really get to the area volume since it's been a while since we spent time with area volume. So let's go to page 12. I want to see how much of that I can get through with you. So if you look at the very back of your packets, I have a couple of formulas that I want us to be able to want us to remind you of. Remember, area for functions is top minus bottom. Area for equations are right minus left. If we do top minus bottom, everything has to be in terms of x, or balance in terms of x, or expressions in terms of x. This method would be find the radius, and then we do the base length squared. For washer method, we have two separate extensions, and we have to build both the radius, either top minus bottom or right minus left. And the cross sections, yeah, we can definitely review that as well. So, number 14. Okay, it says let region R be in the first quadrant, bounded by the graph y equals x squared and y equals root x. So in the first quadrant, so I'm going to go ahead and draw those two graphs. You have y equals x squared, that's a parabola. I only care about what it looks like in the first quadrant. And I also have y equals square root of x, that's a radical function. So it's going to look more like this. So there's my shaded region. The y equals square root of x is the one that's on top here. Okay, R is the base of a solid whose cross section perpendicular to the x-axis are squares. What is the volume of the solid? So we're not rotating around anything. We're actually building a shape, a squares on top of this base. So this shape has no bearing. We're building squares that sit on top of that shape. So first thing we do is we just have to, so there's no rotation, there's no axis of revolution, there's no radius. We just want to draw the base exactly how they describe it. So it says perpendicular to the x-axis. So which direction is that? Perpendicular to the x-axis. Vertical or horizontal? Vertical. Okay, so you're not going to have to do any rotation. So it's not like we got to draw the radius and you got to draw something perpendicular to it. You're just going to draw exactly this direction that they have. Okay, so this is going to represent the base of a square. So imagine this is on the sheet of paper and you're building squares that's coming out of the page. And then once you accumulate that, then whatever that funny looking shape is, that's the volume that we're looking for. Okay. Now we see a vertical base length in front of us, so we can just simply find the base by doing top minus bottom. The nice thing about top minus bottom is we don't have to do any adjustment. Everything that we see in front of us is ready for us to use. So the top minus bottom, what's the top of the base length touching? Root x. Minus, what's the bottom of this vertical length touching? X squared, yeah. So that's the base length. Next up, we want to build the area. The area is squares, and the formula for squares is base quantity squared. And then to get from area to volume, we just attach the integral on both sides of the area. So volume is just the definite integral of the area dx. Okay. So we start off with the one-dimensional, then we get to the two-dimensional, and then we get to the three-dimensional. We're just kind of building everything on top of each other. Okay. Now to find the volume, we do need to find the bounds. So the bounds is from 0 to whatever that intersection is. So you can use your calculator, find that intersection, but it ends up being an easy value. It's actually just x equals 1. So my volume is just a definite integral. Notice that there's no pi in front. There's no rotation. It's not disk or washer method. So if there's no rotation, there's no circle involved. There's no circle involved. There's no pi in front. So the base is root x minus x squared. We want to square the entire base length, dx from 0 to 1. Okay, just make the calculator do all the work for you there. Volume is 0.12. It's not. Okay, 15. Another cross-section problem. The base of a solid is the region enclosed by the graph y equals sine x squared and the x-axis. So if you use your calculator, you can see that it's going to look something like this. Between 0 and root pi. It says the cross-section perpendicular to the x-axis. So again, which direction is that? Vertical. Okay. So the nice thing about vertical is, again, no rotation here. We're just going to build the base with what we see in front of us. Okay. So the base is simply top minus bottom. The top of this vertical length is touching the curve. The bottom is sitting at the 0. So it's sine x squared minus 0, which is sine x squared. Again, we're dealing with squares, so area is just base squared. And the volume is just taking the area and putting an integral around it. Okay, so pretty much the same setup as the previous problem. Okay, number 16, let R be the region enclosed by the graph of 4 over x and the line 5 minus x. Use your calculator to see what that looks like. But now you see the word revolving. So that means there's going to be an axis, there's going to be a radius. We know it's either disk or washer method. Now we got to have that dotted line and all that. Okay, so 4 over x is kind of a curve, and 5 minus x is a line. So 5 minus x is a linear graph with negative slope. And 4 over x kind of has a rational function feel to it. So it looks like this. Okay, we're going to rotate this shaded region around the y-axis. So That's where our dotted line is going to live. Okay, look at the fact that it's a vertical axis of revolution. Which, how is our radius going to look? Vertical or horizontal? Horizontal, right? It's got to extend from the axis. And is this going to be a disk or washer method? Washer, right? There's a definite gap, right? There's no, it's not up against the flat surface of the shaded region. So we have to draw two radius, one that extends to the furthest boundary, one that extends to the closer boundary. Now, what's the red flag that we always have to be aware of anytime we see right minus left? We use the equations as they stand, the 4 over x and the 5 minus x. We have to, put it in terms of, right, so we got to say x equals, and what shows up needs to be in terms of, well, yeah, basically say the right size in terms of y. So I have to rewrite these equations here. Y equals 4 over x. I have to cross multiply. This is not solve for the correct variable. So if I cross multiply here, I get xy is equal to 4. So x equals 4 over y. So that's the curve. Okay, now the linear equation, the y equals 5 minus x. If I solve for x, I can say x equals 5 minus y. So that's the line. Okay, so we got to use these equations and the axis of revolution to build our radius. Okay, so let's build our radius, big R. Okay, right minus left. The right endpoint is sitting on the line. The left endpoint is sitting at the y-axis. So 5 minus y minus 0. Small radius, little r. Right endpoint is sitting at the curve, which is the 4 over y. The left endpoint is sitting on the y-axis, so that's a 0. So my volume formula is big radius squared minus little radius squared. And my bounds have to be in terms of what? X or y, in terms of y. So we have to use the calculator, find those intersections, find those y values. Ends up being a y value of 1 and a y value of 4. So big radius, quantity squared, minus little radius, quantity squared. Make sure there's a pi in front. Now we are rotating. And then lowest y value is 1, highest y value is 4, and that matches answer choice C. Okay, let's try number 17. What is the volume of the solid generated when the region bounded by the graph x equals root y minus 2 and the line x equals 0 and x equals 5 revolving around the y-axis? So if it doesn't feel familiar to you, you can always solve in terms of y, square both sides. So it's really x squared minus 2. That's a parabola. With the y-intercept of 2. So you see that positive square root indicates that it's just the positive portion of the parabola. So it's between this curve, y equals 5, and the y-axis. So it's going to be this kind of looks like a quarter looking circle, shaded region. You're rotating that shaded region around the y-axis. Which direction is the radius going to extend? Will radius be top minus bottom or right minus left? Right minus left. And what are we dealing with here? Is this method or washer method? This method. You see how that dotted line is right up against the flat surface? So there's only one radius needed, so just big R squared. Adjustment that's needed is we have to get everything in terms of Y. Well, the nice thing is this is already given to us in terms of Y on the right side, so we can use that. Your equations will have a very specific look to it. The left side of your equations will all be in the form of x equals, and then you're using the term on the right side. Okay. Our bounds, we can tell what's the lowest and highest Y value on the shaded region. Okay. Lowest Y value is 2, the highest Y value is 5 from that horizontal line. Okay, so then our big radius, right minus left. And then we'll just put it into our this method formula. Big radius squared. And you can plug this in the calculator. But notice that on paper it's in terms of Y, but in your calculator you're only using X's. So in this case, looks like they want you to multiply that pi through to get a decimal that matches the answer choice. So answer choice E. I don't want to make sure that I got through area and volume. I think a good review is looking over your chapter 7 test. And if you can, if you feel good about the test, you should feel good about area and volume in general. I kind of skipped around between 9 and 12, but I think tomorrow I can spend more time going over the specifics, going over more pages 9 through 11. But I wanted to get through area and volume and kind of make you guys see all the different variations and make sure we still remember it. Okay, let's go and get your phones. Tomorrow morning, I will have a help session going over pages 19 through 22 in your packet form. So, yeah. Yeah. I'll check the rest on Friday. Subject to.
So we're allowed.
You got it.
We would have to like. Because.
I think students can stay in the cafeteria.
Well, like it's after I'm gym, I don't like go from.
Yeah. You can come down.
Is there a previous recorded video for this help session, like there was on the last one on your?
Yes, yeah. It should be there already.
Yeah.
But I will share a link today.
Okay, thank you.
Yeah.